Every point of light in the cosmos hides a truth that could shatter our understanding of reality. We will explore 25 deep space phenomena that do exactly this, from the grip of black holes to the push of dark energy. By the end, you will see the universe not as a static backdrop, but as a dynamic, mysterious entity that constantly challenges our fundamental laws. What if the very fabric of space and time is not what it seems? And why does most of the universe remain completely invisible to us? How does it feel to know that everything you see in the night sky is just a fraction of the real story at the heart of our own galaxy? A silent titan waits. This is Sagittarius, a star, a supermassive black hole with a gravitational pull so intense it bends the very fabric of space and time around it. These are not the empty voids they are sometimes mistaken for, but incredibly dense objects where matter is crushed into a point of infinite density. Their mass is almost incomprehensible, ranging from millions to billions of times the mass of our Sun. They anchor entire galaxies, governing the orbits of billions of stars through their invisible, overwhelming influence. We cannot see them directly, for they trap light itself, but we witness their ferocious effects. Stars whip around them at dizzying speeds, and vast disks of superheated gas swirl at their edges, glowing with intense radiation. When these black holes feed, they can unleash quasars, beacons of energy so brilliant they outshine every star in their home galaxy combined. The very existence of such giants so early in the universe's life poses a monumental challenge to our models of cosmic evolution. How could they grow so large so quickly? When the Event Horizon Telescope captured the first image of a black hole's shadow, it was not a picture of the object itself, but of its dark silhouette against the fiery backdrop of its accretion disk. This confirmed predictions made by Einstein's theory of general relativity a century earlier, yet it also deepened the central mystery. What ultimately happens to all the matter and information that crosses the event horizon, the point of no return? The laws of physics, as we understand them, suggest it is lost forever, a notion that conflicts with other fundamental principles. If time slows to a crawl and space is stretched into spaghetti like strands near a black hole, what does that say about the true nature of our reality? This gravitational paradox leads us directly to another cosmic riddle, one that involves not a pull but a push, a force that operates on the grandest scales imaginable. That gravitational paradox leads to a substance so pervasive it forms the cosmic scaffolding of the universe itself, yet it remains completely invisible to our eyes and our finest instruments. This is dark matter. We know it is there only by the ghostly grip of its gravity. Without it, our galaxies would fly apart. Stars on the outer edges of spiral galaxies rotate at speeds that should fling them into the void, yet something holds them in place, something with immense mass that we simply cannot see. The pioneering astronomer Vera Rubin meticulously charted these unexpected rotation curves, providing some of the strongest early evidence that the universe is dominated by a form of matter that does not interact with light. It neither emits, absorbs, nor reflects it. This invisible component makes up roughly 27% of the entire mass-energy content of the cosmos, a staggering 5 times more abundant than all the ordinary matter, the stuff of stars, planets, and us put together. One of the most compelling pieces of evidence comes from cosmic collisions like the Bullet Cluster. When 2 galaxy clusters slammed into each other, the hot gas of normal matter, detected by X-ray telescopes, was slowed and separated from the bulk of the mass, which was mapped through its gravitational lensing effect. The dark matter just sailed right through the collision, demonstrating that it does not interact with itself or with us in any way except through gravity. For decades, scientists have searched for the particle responsible with candidates like WIMP, or weakly interacting massive particles and actions, but so far, it has eluded every direct detection experiment. How does the dominance of an invisible substance alter our perception of the material world? It forces a humbling realization that everything we see and touch is just a minor component of reality, a mere trace element in a vast, dark cosmos. And just as we grapple with this invisible force holding the universe together, we must confront its mysterious counterpart, a force that is doing the exact opposite, tearing the cosmos apart. This mysterious counterforce to gravity revealed a cosmos in runaway expansion, a discovery so profound it upended our vision of cosmic destiny. Dark energy is the name we give to whatever is causing the universe to not just expand, but to do so at an ever-increasing rate. Think of it like a car that, instead of slowing down after you take your foot off the gas, starts inexplicably accelerating faster and faster. This finding was so revolutionary that it earned the two leading research teams the Nobel Prize in Physics in 2011. They reached this conclusion by observing distant stellar explosions known as Type 1, a supernova, using them as cosmic mile markers to measure the expansion history of the universe. To their astonishment, the most far-flung supernovae were dimmer than expected, meaning they were farther away than any model predicting a slowing expansion could account for. The only possible explanation was that a repulsive force, a kind of cosmic antigravity, had been dominating the universe for billions of years, pushing galaxies apart with gathering strength. This dark energy now makes up a staggering 68% of the entire mass energy content of the cosmos. One leading theory connects it to a concept Einstein himself once proposed and then discarded: the cosmological constant, an intrinsic energy woven into the very fabric of empty space. If this vacuum energy is real, then even the deepest, purest void is not truly empty, but seething with a faint, repulsive power. Physicists like Sean Carroll describe it as a fundamental cosmic repulsion that overwhelms gravity's attractive pull across the vast distances between galaxy clusters. The implications for the far future are stark. If this acceleration continues unchecked, it points toward a cold and lonely end for the cosmos. Over trillions of years, galaxies beyond our own local group would recede until their light can no longer reach us, leaving our night sky increasingly barren. The universe would slowly approach a state known as heat death, a vast, dark, and uniform expanse where the fires of stars are long extinguished. This forces us to confront profound questions about the very nature of reality. Is dark energy a constant property of space, or could it evolve over time, potentially tearing the universe apart in a big rip? Could its existence be a clue pointing toward a multiverse, a vast landscape of universes, each with their own unique physical laws? If the universe's expansion is forever accelerating, what does that say about the ultimate fate of all we can see and know? This contemplation of the end is profoundly connected to a whisper from the very beginning, a remnant from the universe's infancy that still echoes through the cosmos today. That faint, cold echo from the beginning of time is the cosmic microwave background radiation. It is the oldest light in the universe, a fossilized remnant from an era when the cosmos was a mere 380,000 years old. Before this moment, the universe was a searing, opaque fog of plasma and energy. As it expanded and cooled, the first stable atoms formed, allowing light to travel freely for the very first time. That initial flash of liberation has been stretching and cooling for almost 14 billion years, and we now detect it as a uniform microwave glow that permeates all of space, bathing the entire universe in a temperature of just 2.7 degrees above absolute zero. Its discovery was a triumph of serendipity. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting persistent static in a giant horn antenna. They famously scrubbed away pigeon droppings, but the annoying hiss remained. It was the same in every direction, a signal that had no earthly source. They had inadvertently stumbled upon the cooled afterglow of creation itself, a finding that earned them the Nobel Prize and cemented the Big Bang as the dominant model of cosmic origins. But this ancient light is far from perfectly smooth. Exquisitely sensitive space telescopes like the Planck mission have mapped its subtle imperfections, revealing a mottled tapestry of tiny temperature differences. These minute fluctuations, variations of just millionths of a degree, are the seeds of all cosmic structure. They are the gravitational blueprints from which every galaxy, every star cluster, and every vast cosmic void would eventually grow. By reading this pattern, cosmologists can answer fundamental questions. The cosmic microwave background tells us the universe is geometrically flat. It confirms the precise age of the cosmos at 13.8 billion years, and it quantifies the amount of ordinary matter, dark matter, and dark energy with stunning precision. It also provides the strongest evidence for cosmic inflation, the theory that the universe underwent an unimaginably rapid exponential expansion in the first fraction of a second after the Big Bang, stretching a quantum speck into a macroscopic cosmos and imprinting those initial wrinkles we see in the background radiation. How does seeing the universe's baby picture change our narrative of cosmic history? It grounds our grand theories in observable data, transforming speculation into a precise cosmic timeline. This primordial echo, a snapshot of the universe's first atoms, connects directly to the story of particles that refuse to interact with matter at all, ghostly travelers that stream through the cosmos unimpeded. Countless cosmic phantoms pass through your body every moment, completely unnoticed. These are neutrinos, subatomic ghosts born in the nuclear hearts of stars, in the violent deaths of supernova, and from the fiery dawn of the universe itself. They are so ethereal that a light year of solid lead would barely slow them down. Their story began with a puzzle. The physicist Wolfgang Pauli proposed their existence to account for missing energy in a type of radioactive decay called beta decay, half-jokingly suggesting he had done a terrible thing by predicting a particle that could not be detected. He called it a desperate remedy, a particle with no charge and seemingly no mass. For decades, it remained a theoretical ghost. We now know neutrinos are real, and they come in three distinct types or flavors: electron, muon, and tau. But the real surprise came when we discovered they are shapeshifters. A neutrino produced in the Sun as an electron neutrino can transform into a muon or tau neutrino on its way to Earth. This phenomenon, called neutrino oscillation, was a monumental discovery. It proved that these phantoms must have some tiny amount of mass, a finding that shook the foundations of the standard model of particle physics, which had long assumed they were massless. To catch these phantoms, scientists build colossal traps. The Super Kamiok and detector in Japan is a tank filled with 50,000 tons of ultra-pure water, lined with sensitive light sensors, waiting for the rare flash of blue Cherenkov radiation created when a neutrino actually interacts with an atom. Far deeper, the Ice Cube Observatory at the South Pole uses a cubic kilometer of ancient Antarctic ice as its detector, watching for the same fleeting flashes. These instruments have opened a new window on the universe's most violent events. When a star explodes as a supernova, the vast majority of its energy is released not in light, but in a tremendous pulse of neutrinos, a ghostly tsunami that precedes the visual fireworks. In 1987, detectors on Earth recorded a handful of neutrinos from a supernova in the Large Magellanic Cloud, providing direct insight into the cataclysmic engine of a stellar death. More recently, IceCube has pinpointed high-energy neutrinos coming from active galactic nuclei and blazars, monstrous black holes powering distant galaxies. These particles, traveling for billions of years without being deflected by magnetic fields or absorbed by dust, point directly back to their violent origins. They are cosmic messengers carrying information from places light cannot easily escape. They were also essential architects of our material world. The intense flood of neutrinos in a supernova explosion helps blast the newly forged heavy elements out into space, seeding the cosmos with the building blocks for planets and life. How does this constant, silent rain of intangible particles alter your sense of reality? Your body, the chair you sit on, the very air you breathe, are mostly empty space to these phantoms. They redefine solidity as a fragile illusion, a temporary congregation of matter in a cosmos dominated by the intangible and unseen. And the most violent cosmic events that produce these ghosts also create something far more extreme, ripples in the very fabric of the cosmos itself. The universe's most violent explosions leave behind a silent rain of phantoms, but the blasts themselves are brief, terrifying flashes of pure power. Gamma-ray bursts are the most energetic events known to exist since the Big Bang itself. In just a few seconds, a single burst can release more energy than our Sun will emit across its entire 10 billion-year lifetime. For decades, these events were one of astronomy's greatest puzzles. They appeared as random, fleeting signals on military satellites designed to monitor for nuclear tests, brief spikes of intense gamma radiation coming from seemingly random directions in the sky. We now know these bursts are cosmic beacons signaling the birth of black holes and the collision of dead stars. They are divided into two main types, each with a different cataclysmic origin. Long-duration bursts lasting from 2 seconds to several minutes are thought to be the death cries of massive, rapidly spinning stars. When such a star exhausts its nuclear fuel, its core collapses directly into a black hole. This collapse triggers the formation of ultra-focused jets of particles and radiation that blast outward at nearly the speed of light. If one of these jets is pointed directly at Earth, we see it as a brilliant gamma-ray burst. The shorter bursts, lasting less than 2 seconds, are even more extreme. They are believed to result from the violent merger of two neutron stars, or a neutron star and a black hole. When these incredibly dense objects spiral into each other, they too can create a black hole and launch relativistic jets, unleashing a flash of gamma rays and shaking the very fabric of spacetime. The true breakthrough in understanding came from studying their afterglows. After the initial flash fades, the interaction of the jets with surrounding gas creates a fading ember that can be observed for days or weeks across other wavelengths, from X-rays to radio waves. This afterglow allows astronomers to pinpoint the burst's host galaxy and measure its immense distance. One event in particular, known as GRB 170817A, marked a historic turning point. In August 2017, gravitational wave observatories detected ripples in spacetime from a neutron star merger. Just 2 seconds later, satellites observed a short gamma-ray burst from the same patch of sky. For the first time, we had witnessed a cosmic cataclysm with both light and gravitational waves, a new era of multi-messenger astronomy. This single event confirmed the origin of short gamma-ray bursts and provided a wealth of data, revealing the forge where heavy elements like gold and platinum are created. What do these unimaginable explosions teach us about the limits of energy and matter? They show us that matter can be transformed into pure energy with an efficiency far beyond our most powerful reactors. and that the birth of a black hole is a process of both creation and destruction. These bursts act as probes, their light traveling across billions of years, allowing us to study the conditions of the early universe and test the laws of physics under the most extreme conditions imaginable. The remnants of such violence are often objects of impossible density, where the rules of physics as we know them are pushed to the breaking point. The remnants of a supernova can leave behind a city-sized object of impossible density. This is a neutron star, a stellar corpse where matter has been crushed into a state beyond our everyday comprehension. A single sugar cube of its material would weigh billions of tons on Earth, a mass comparable to that of every human being combined. These objects are the collapsed cores of massive stars that have exhausted their fuel, packing more mass than our entire sun into a sphere no wider than a small city. Within this incredible density, protons and electrons are forced together, merging into a sea of neutrons so tightly packed that the star is essentially a single, gigantic atomic nucleus. The conditions are so extreme that the very nature of matter itself becomes a mystery. How does material behave when it is compressed to such a degree? We simply do not know what bizarre states of matter might exist in its core, with some theories suggesting a soup of free quarks or other exotic particles. Their influence does not end with their incredible density. Neutron stars also possess magnetic fields of almost unimaginable strength, trillions of times more powerful than Earth's. This ferocious magnetism can strain the star's crust, leading to starquakes that release immense flashes of energy, events we detect as sudden, powerful X-ray bursts. Some of these objects reveal themselves as pulsars, cosmic lighthouses. As the neutron star spins at dizzying speeds, sometimes hundreds of times per second, powerful beams of radiation shoot from its magnetic poles. If these beams sweep across Earth, our telescopes register them as a perfectly steady, repeating pulse. The discovery of the first pulsar in 1967 was a landmark moment. A young researcher named Jocelyn Bell Burnell noticed a curious, rhythmic signal in her radio telescope data, a pulse so precise it was initially nicknamed LGM for Little Green Men. Her careful work confirmed it was a natural phenomenon, providing the first direct evidence for the existence of neutron stars. These objects are not just static relics. When two neutron stars orbit each other in a binary system, they lose energy by emitting gravitational waves, those ripples in space-time, slowly spiraling inward until they collide in a cataclysm that also produces a short gamma-ray burst. The historic observation of such a merger in 2017 confirmed that these violent events are the universe's primary forges for heavy elements. The immense pressures and densities of the collision create a nuclear furnace, producing vast clouds of gold, platinum, and other precious elements, scattering the building blocks of planets and life across the cosmos. Neutron stars serve as unparalleled natural laboratories, allowing us to test the laws of physics under conditions we could never recreate on Earth. They push our understanding of nuclear matter and gravity to the absolute limit, standing as a testament to the universe's ability to create objects of both terrible beauty and profound mystery. A neutron star's magnetic field can be so powerful it warps the very atoms in its vicinity. These are magnetars, a rare and volatile class of neutron star where magnetic forces reach almost unimaginable extremes. Their magnetic fields are up to 1,000 times more intense than those of ordinary neutron stars, and quadrillions of times stronger than Earth's. If you could bring one halfway to the moon, its magnetic influence would be strong enough to strip the data from every credit card on our planet. These cosmic powerhouses are thought to form when the core of a particularly massive and rapidly spinning star collapses during a supernova, concentrating a dying star's magnetic energy into an object just a dozen miles across. The immense stress of such a magnetic field can literally crack the star's rigid crust, causing catastrophic starquakes. These seismic events on the magnetar's surface unleash colossal flares, sudden and terrifying releases of energy. In December 2004, a magnetar named SGR 180620 produced a giant flare. For a mere tenth of a second, it released more energy than our Sun emits across 100,000 years. This explosion, originating from 50,000 light-years away, was still powerful enough to measurably affect Earth's upper atmosphere, briefly ionizing a layer and temporarily disrupting long-range radio communications. It was a stark reminder of the raw power that exists in the distant cosmos. Studying these outbursts gives us a unique laboratory for testing physics under conditions we can never hope to recreate. The behavior of matter and energy in such ferocious magnetic fields challenges our understanding of quantum electrodynamics, pushing the very theory of how light and matter interact to its absolute limit. Some researchers now suspect that the sudden magnetic reconnection events on magnetars could be the source of some fast radio bursts, those mysterious millisecond-long blips of cosmic radio energy. What can such ultra-strong magnetic fields teach us about the fundamental forces that knit our universe together? They reveal a realm where magnetism ceases to be a simple force and becomes a dominant, shaping power over reality itself. And just as these intense magnetic events can unleash brilliant flashes, other, far more subtle signals drift across the cosmos, whispers that seem to defy all explanation. A flash of radio light brighter than 500 million suns appears and vanishes in less than the blink of an eye. These are fast radio bursts, cosmic enigmas that pour out immense energy only to disappear without a trace. Their story began quietly, hidden in archival data from 2007, when an astronomer sifting through old observations found a spike of radio waves so powerful and so brief it had been overlooked. Since that first discovery, hundreds of these fleeting signals have been detected, each one a brief scream of energy from a distant galaxy. The sheer power involved is staggering. A single millisecond burst can release more energy than our Sun emits over many days, but perhaps the most perplexing characteristic is that some of them repeat. While many are one-off events, a handful, like the famous FRB 121102, fire off again and again from the same patch of sky, yet with no predictable pattern. This repetition rules out any explanation that involves the total destruction of the source, like a single cataclysmic collision. So what cosmic engine can produce such intense, focused energy in a recurring, unpredictable way? The leading suspects are magnetars, those neutron stars with unimaginably powerful magnetic fields. A starquake on a magnetar's surface, a sudden snapping of its magnetic field lines, could potentially unleash a focused blast of radio waves powerful enough to explain these signals. Other theories point to the mergers of neutron stars or the violent accretion of material onto a black hole. The diversity of the bursts we observe suggests that there may not be one single answer, but a whole family of cosmic phenomena capable of producing these brilliant radio flashes. What makes these signals more than just a mystery is their utility. As a fast radio burst travels across millions or billions of light-years, its different radio frequencies are slowed by the thin plasma that drifts between galaxies. This delay, called dispersion, allows astronomers to measure the total amount of invisible material the signal has passed through. Each burst becomes a probe, charting the vast, diffuse cosmic web of ionized gas that is otherwise nearly impossible to see. They illuminate the lonely highways between galaxies. What do these split-second cosmic broadcasts tell us about the universe's hidden, energetic heartbeat? They remind us that the cosmos is filled with transient, violent events that operate on timescales far beyond human perception, flickering in and out of existence in an instant, yet carrying the signature of the largest structures in existence. These brief radio whispers are complemented by some of the most visually stunning and enduring structures the universe has to offer. A massive object in space can bend light like a giant lens, creating ghostly mirages of distant galaxies. This is gravitational lensing, a dramatic confirmation that mass warps the very fabric of spacetime, as Einstein's theory of general relativity predicted. The path of light, which we often think of as perfectly straight, is forced to curve as it travels through the distorted geometry around a galaxy cluster or a black hole. This cosmic trick of the light gives us three distinct flavors of observation. Strong lensing creates spectacular, unmistakable arcs, rings, and even multiple copies of the same background galaxy. The Hubble Space Telescope's image of Able 1689 is a breathtaking example, a cluster so massive it smears the light from hundreds of distant galaxies into a tapestry of luminous streaks and crescents. Then there is the Einstein Cross, a perfect celestial alignment where a single distant quasar appears as four distinct images arranged around a closer galaxy, a stunning demonstration of spacetime's curvature. Weak lensing is more subtle, a statistical warping that causes thousands of distant galaxies to appear slightly stretched and aligned, as if seen through a vast, rippled pane of glass. By measuring this collective distortion, astronomers can map the distribution of dark matter, tracing the invisible cosmic scaffolding that holds the universe together. The third type, microlensing, occurs when a single star or planet passes in front of a more distant star. The foreground object's gravity briefly acts as a tiny magnifying glass, causing the background star's light to brighten and then fade in a specific telltale pattern. This method has proven incredibly powerful for discovering exoplanets that would otherwise remain hidden, including rogue planets drifting alone in the dark between stars. How does the bending of light by invisible mass reshape our view of the cosmos? It transforms the universe into a dynamic, funhouse mirror, where distortions are not flaws but features, revealing the hidden architecture of reality. This cosmic magnification routinely reveals galaxies from the early universe that are so massive and structured, they defy conventional models of formation, forcing us to reconsider the timeline of cosmic evolution. And just as light can be warped by gravity, so too can the flow of time itself, a phenomenon that becomes starkly apparent in the presence of a truly monstrous cosmic anchor. Two colossal bubbles of energy tower above and below the Milky Way, each reaching 25,000 light-years into the void. Known as the Fermi Bubbles, these vast structures are invisible to our eyes but glow intensely in high-energy gamma rays and X-rays, a discovery made by the Fermi Gamma Ray Space Telescope that revealed a dramatic chapter in our galaxy's history. They form a perfect hourglass shape, erupting symmetrically from the galactic core, a clear sign of some titanic explosion in our relatively quiet neighborhood. The leading theory points to our resident supermassive black hole, Sagittarius, a star. In the distant past, it may have gone through an active phase, feasting on immense amounts of gas and dust. This feeding frenzy could have generated powerful jets of radiation and matter, inflating these giant lobes like cosmic balloons over millions of years. An alternative possibility is a period of intense star formation near the center, leading to a chain reaction of supernova explosions whose collective shockwaves blew this massive structure into being. Whatever the cause, the Fermi bubbles present a major challenge to our understanding of galactic feedback. the process by which energy from a galaxy's core regulates star formation and heat across vast distances. How does such a tremendous release of energy travel so far and shape the galaxy's evolution without simply dissipating into the void? These structures are not unique to the Milky Way. Astronomers have spotted similar giant bubbles and radio lobes emanating from the hearts of other galaxies, suggesting this is a common, if episodic, phase in a galaxy's life. They act as cosmic archives, their size and energy content recording the timing and ferocity of the ancient outburst that created them. By studying the bubble's edges and the hot gas within them, scientists can probe the conditions of the interstellar medium, the thin soup of gas and cosmic rays that fills the space between stars. What do these silent, towering remnants tell us about the violent past of our seemingly calm galaxy? They are a fossilized eruption, proving that even a quiet cosmic home like the Milky Way has experienced cataclysmic growing pains, with its central black hole occasionally waking to reshape its entire environment. This evidence of large-scale structure within our own galaxy hints at even more expansive and mysterious patterns woven into the cosmos itself. A mysterious force is pulling our entire galaxy and its neighbors on a relentless journey through the cosmos. This is the Great Attractor, a gravitational focal point of almost unimaginable scale, located in the distant constellation of Centaurus. For decades, astronomers were puzzled by the peculiar velocities of galaxies in our local universe, including the Milky Way. Instead of moving solely with the uniform expansion of space, thousands of galaxies are streaming toward this single region at speeds exceeding 2 million kilometers per hour. The sheer mass required to orchestrate this motion is staggering, equivalent to tens of thousands of Milky Way galaxies concentrated in one area of intergalactic space. Yet for a long time, its true nature was hidden from our view, lying directly behind the crowded, dusty central plane of our own galaxy, a region astronomers call the zone of avoidance. Our optical telescopes were essentially blind to what lay beyond this celestial barrier. The breakthrough came with eyes that could see through the dust. Infrared surveys like those from the 2-micron all-sky survey and radio telescopes peering through the cosmic murk began to map the hidden architecture. They revealed that the Great Attractor is not a single, monstrous object, but a colossal confluence of mass anchored by the Neutrino Cluster, a dense swarm of galaxies, and part of an even larger supercluster known as Laniakea. This discovery redefined our cosmic address, showing that our Milky Way is merely a suburban resident on the outer fringes of this immense gravitational metropolis. How does a hidden gravitational focal point influence our journey through the cosmos? It demonstrates that the serene expansion of the universe is overlaid with violent, local currents and tides, where titanic concentrations of matter, both seen and unseen, dictate the motion of galaxies on epic scales. This immense pull is just one part of an even vaster and more mysterious cosmic flow. Our local journey toward the Great Attractor is just one small current within a vaster cosmic river. This immense flow is part of the Laniakea Supercluster, our home on a scale almost too large to comprehend. Encompassing 500 million light-years and containing roughly 100,000 galaxies, Laniakea is a celestial continent, and our Milky Way is a single town within its sprawling borders. Its name, from the Hawaiian language, means immense heaven, a fitting title for a structure that redefines our cosmic address. Before its definition in 2014, we saw our local universe as a collection of separate clusters. But by meticulously mapping the peculiar velocities of galaxies, tracing their subtle movements against the backdrop of cosmic expansion, astronomers revealed a stunning truth. Entire galaxy clusters, including our own local group and the massive Virgo cluster, are all streaming together toward the same gravitational basin, like water droplets flowing down the slopes of a single, vast valley. The identification of Laniakea relied on sophisticated algorithms to decipher these cosmic currents, painting a picture of a dynamic and deeply interconnected universe. It shows us that galaxies are not scattered randomly like isolated islands. Instead, they form a cosmic web, gathering along immense filaments and great walls that trace the underlying scaffolding of dark matter. These luminous structures are separated by even vaster regions of near emptiness, cosmic voids that stretch for hundreds of millions of light years. What does it mean to belong to such an immense, flowing structure? It profoundly recontextualizes our place in the cosmos. We are not just residents of a galaxy, but participants in a grand, gravitational dance on a scale that dwarfs human imagination. Our local supercluster is one thread in this universal tapestry, a single pattern in a fabric woven from both brilliant light and profound emptiness. These colossal voids between the threads hold mysteries of their own. These immense, silent voids are the true rulers of cosmic geography. Vast regions of near-nothingness stretch for hundreds of millions of light years, dwarfing the brilliant filaments and walls of galaxies. These are cosmic voids, and they dominate the large-scale structure of our universe, making up over 80% of its volume. The most famous of these is the Boötes void, a spherical emptiness so vast it could contain thousands of galaxies like our Milky Way. Yet astronomers have found only a handful of isolated islands of stars within its borders. The existence of such profound emptiness was a shock to cosmologists. When the first maps of the cosmic web were drawn, the expectation was a fairly even distribution, like a sponge. Instead, we found a universe structured like a collection of soap bubbles, with galaxies clinging to the thin surfaces and the interiors almost completely vacant. This presented a major challenge to our models of how structure formed after the Big Bang. How could gravity, an attractive force, have sculpted such expansive regions of avoidance? The answer lies in the very beginning. The minuscule quantum fluctuations imprinted on the cosmic microwave background provided the seeds. In regions of slightly lower density, there was less matter to gravitationally attract, causing those areas to fall behind in the cosmic race to form structure. Over billions of years, these underdensities grew into the colossal voids we observe today. These spaces are not perfectly empty, of course. They contain a sparse soup of extremely diffuse hydrogen gas and most likely the ubiquitous presence of dark matter, though in much lower concentrations than in the galactic filaments. The true dynamism of a void comes from its expansion. While the universe as a whole is expanding, the space within a void stretches faster than average, creating a kind of local acceleration that is separate from dark energy. This regional push influences the motion of galaxies at the void's edges, gently shepherding them toward the denser walls. This makes voids incredible natural laboratories for studying the nature of gravity and the influence of dark energy on different cosmic environments. Because they are so much simpler than the chaotic knots of galaxy clusters, their evolution is easier to model and compare with theoretical predictions. How do these immense empty spaces affect the evolution and distribution of galaxies? They act as cosmic pressure chambers, their expanding boundaries helping to define the great walls and filaments. And within these lonely expanses, the rare galaxies that do form are often strange and pristine, having evolved in isolation for billions of years, untouched by the violent mergers and interactions that shape their cousins in the crowded clusters. These isolated galaxies offer a unique glimpse into a quieter, more solitary path of cosmic evolution. Some galaxies are vast, silent, and almost invisible. These are the ultra-diffuse galaxies, cosmic phantoms as wide as the Milky Way but containing only 1% of its stars. Their light is so faint they can hide in plain sight, drifting through crowded galaxy clusters or floating in the profound isolation of cosmic voids. For a long time, our telescopes simply looked past them, their gossamer glow lost in the stellar brilliance of their neighbors. The discovery of objects like Dragonfly 44 revealed just how much we had been missing. This particular ultra-diffuse galaxy has the mass of our own Milky Way, but its stars are spread so thin that the entire structure is practically transparent. The only way to explain its immense gravitational pull, which holds it together despite its ghostly appearance, is to conclude it is dominated by a massive halo of dark matter, just like a normal galaxy. This presents a profound puzzle. Why would a galaxy with all the gravitational scaffolding for a brilliant metropolis of stars remain so dark and quiet? It suggests that the process of galaxy formation has many more outcomes than we ever imagined. Some of these faint giants may be failed galaxies, systems that formed early on but had their gas stripped away by the fierce gravitational tides of a cluster or by internal feedback before most stars could ignite. Others might be ancient relics surviving for billions of years in a state of arrested development. Adding to the mystery, instruments like the Hubble Space Telescope and the Keck Observatory have found that some ultra-diffuse galaxies are surprisingly rich in globular clusters, those dense, ancient swarms of stars. This is deeply unusual, as the number of globular clusters typically correlates with the mass of a galaxy's dark matter halo. To find so many of these clusters in such a faint galaxy implies that its dark matter content is indeed vast, yet for some reason, that dark matter failed to gather the gas needed to light up with new stars. Why do some galaxies possess the dark matter framework for a stellar empire, yet choose to live in near darkness? These cosmic enigmas force us to reconsider the very recipe for a galaxy, revealing that dark matter's gravitational influence does not guarantee a bright, stellar life. They are the shadow counterparts to the universe's most luminous objects, proving that cosmic reality encompasses both brilliant beacons and vast, quiet ghosts. An ancient beacon shines from the edge of time, a single point of light outshining a trillion suns. These are quasars, the intensely bright cores of distant galaxies, where a supermassive black hole feasts on a torrent of gas and dust. The energy released is so staggering it can be thousands of times brighter than the entire Milky Way, a brilliance that makes the surrounding galaxy seem like a faint, hazy afterthought. When first identified in the 1960s, these quasi-stellar radio sources appeared as star-like pinpricks on photographic plates, but their spectra told a different story. Their light was dramatically shifted toward the red, a clear sign they were racing away from us at tremendous speeds, placing them billions of light-years distant. We now understand we are witnessing the violent teenage years of galaxy formation, a phase when the central black hole is actively growing, pulling matter into an orbiting disk of superheated plasma. As this material spirals inward, friction heats it to millions of degrees, causing it to glow fiercely across the entire electromagnetic spectrum, from radio waves to X-rays. This makes quasars the most powerful and efficient engines in the universe, converting matter into pure energy with a ferocity that defies earthly comparison. Their light does not travel to us unimpeded. As it journeys across the cosmic void, it passes through clouds of diffuse gas, each cloud imprinting its own unique signature on the quasar's spectrum. These absorption lines act like a cosmic barcode, allowing astronomers to dissect the composition and temperature of the invisible material that drifts in the vast spaces between galaxies. Every quasar spectrum is a fossilized record of its long journey, a detailed map of the intergalactic medium. How do these ancient powerhouses illuminate the conditions of the young universe? They serve as backlights, their incredible brightness piercing the cosmic fog to reveal the structure and content of the early cosmos. Their variability poses another profound challenge. A quasar can double its brightness in a matter of days or weeks, which means the immense energy-producing region must be incredibly compact, no larger than our own solar system. How can such a small volume generate so much power? The only plausible answer involves the awesome physics of accretion onto a black hole, a process we are still striving to fully comprehend. Some quasars also launch colossal jets of plasma, stretching for millions of light years and moving at nearly the speed of light. These relativistic outflows channel immense energy into the surrounding intergalactic space, heating gas and effectively shutting down star formation in their host galaxies. This feedback process is crucial, revealing a deep symbiotic relationship between a growing black hole and the evolution of its galactic home. The light that finally reaches our telescopes today began its journey when the universe was young, offering us a direct window into an era of cosmic construction and chaos. In the deep darkness of the early universe, colossal clouds of glowing gas began to condense, structures so vast they could swallow our entire local group of galaxies. These are Lyman-Alpha Blobs, immense and luminous clouds of primordial hydrogen, each one spanning hundreds of thousands of light years. They glow with a specific, haunting emission, a spectral signature of hydrogen gas being energized by powerful, hidden forces. For a long time, they appeared as faint, extended smudges in the deepest astronomical surveys, their true nature a mystery. We now understand they are cosmic incubators, often found at the hearts of forming galaxy clusters, where the first massive structures were being assembled. The source of their incredible glow is a subject of intense study. It could be the fierce ultraviolet light from bursts of newly formed stars within protogalaxies, radiation so intense it makes the surrounding hydrogen gas fluoresce like a cosmic neon sign. Alternatively, the energy might be pouring from active galactic nuclei, the furious black holes at the centers of infant galaxies, blazing as they consume matter. A third possibility is that the glow comes from the gas itself cooling and releasing its gravitational energy as it flows into these vast cosmic potential wells. Observatories like the Subaru telescope have mapped their incredible extent, while the Atacama Large Millimeter Array, or ALMA, has peered into their hearts, revealing dense knots of gas that are the birthplaces of future galactic giants. These blobs are not just passive clouds, they are active construction sites where gas is being funneled along cosmic filaments to feed the growth of the universe's first major galaxies. What do these primordial gas clouds reveal about the assembly of the first large structures? They show us a universe in its most dynamic and formative phase, where the invisible scaffolding of dark matter was pulling vast reservoirs of neutral hydrogen together, setting the stage for everything that would follow. Their very existence, so early in cosmic history, hints at how the initial rapid expansion of the universe planted the seeds for these immense gaseous embryos, allowing them to collapse into the great walls and clusters we see today. This process of cosmic construction from diffuse clouds leads us to ponder an even more elusive state of matter, one that is theorized to form the very core of the most extreme objects in existence. The universe we observe today, vast and varied, owes its very existence to a fleeting moment of unimaginable growth. In the first sliver of a second after the Big Bang, space itself is thought to have undergone a violent exponential expansion known as cosmic inflation. This was not an expansion of matter into space, but a stretching of spacetime itself, inflating a subatomic quantum speck into a macroscopic cosmos almost instantaneously. This idea, pioneered by physicists like Alan Guth, resolves two of cosmology's greatest puzzles. The horizon problem asks why the cosmic microwave background is so perfectly uniform in all directions. Regions on opposite sides of the sky were never in causal contact, so how did they reach the same temperature? Inflation solves this by suggesting the entire observable universe was once a tiny, connected patch that was stretched to its immense size, preserving that initial uniformity. The flatness problem asks why the geometry of our universe appears so perfectly balanced or flat. Inflation acts like a cosmic magnifying glass, stretching any initial curvature so dramatically that the resulting universe appears flat to our measurements, just as the surface of a balloon appears flatter as you blow it up. This brief but transformative era did more than just smooth and flatten the cosmos. It also planted the seeds for all future structure. The quantum fluctuations that were present in that microscopic patch were stretched to astronomical sizes, becoming the slight variations in density that gravity would later amplify into galaxies, clusters, and the vast cosmic web. This is why the pattern of hot and cold spots in the cosmic microwave background aligns so perfectly with the distribution of galaxies we see billions of years later. While the evidence for inflation is compellingly indirect, the hunt for a direct signature is one of the most ambitious pursuits in modern science. The theory predicts that the violent expansion should have generated a background of primordial gravitational waves, ripples in the fabric of spacetime that would have left a faint, swirling pattern or B-mode polarization in the cosmic microwave background. Experiments across the globe, from the South Pole to high-altitude balloons, are tirelessly scanning the sky for this elusive imprint. The implications of inflation stretch our understanding of reality to its breaking point. If space can inflate once, could it happen repeatedly, giving rise to a multiverse, an endless tapestry of bubble universes with different physical laws? How does such a process fit into a theory of quantum gravity, and what does it say about the very concept of a beginning? Different models of inflation make specific, testable predictions about the precise spectrum of those initial density fluctuations, offering a potential window into physics at energies far beyond the reach of any particle collider. How does a single, brief era of ultra-rapid expansion set the stage for the entire 14-billion-year cosmic history that follows? It establishes the initial conditions for everything, from the largest galaxy clusters to the smallest planetary systems. And that early burst of growth may have left more than just a temperature map. It may have imprinted the universe with the faintest possible echoes, primordial ripples in spacetime that we are only now learning how to hear. The faintest possible tremors still ripple through the cosmos from its violent birth. Primordial gravitational waves are theorized to be these echoes, literal wrinkles in the fabric of spacetime generated during the first fraction of a second of the universe's existence, during the epoch of cosmic inflation. If the cosmic microwave background is the universe's baby picture, then these waves are the sound of its first cry, a fundamental vibration that has been stretching and fading for nearly 14 billion years. Their detection would be the ultimate smoking gun for inflation, providing direct evidence that the universe underwent that incredible, exponential growth spurt. Unlike the gravitational waves from black hole mergers detected by LIGO, which are like splashes in a pond, primordial waves would be a constant, universe-filling hum, a relic of the most energetic event in all of existence. They would allow us to probe physics at energies trillions of times higher than what we can achieve in any particle collider, offering a unique window into the Planck epoch, a time when gravity and the other fundamental forces were likely unified. The primary way to find them is to look for their unique signature imprinted on the cosmic microwave background. As these ancient ripples passed through the primordial plasma, they would have subtly polarized the light, twisting it into a specific swirling pattern known as B-mode polarization. Finding this pattern in the CMB is one of the holy grails of modern cosmology. The hunt has been incredibly challenging. Experiments like BICEP, located at the South Pole to take advantage of the ultra-dry, stable air, initially announced a tantalizing detection, only to find that the signal was contaminated by polarized light from foreground dust within our own Milky Way galaxy. The painstaking work of separating this cosmic signal from local interference continues, with observatories becoming ever more sensitive. What would it mean to finally detect these echoes from the universe's first moments? It would tell us not just that inflation happened, but how it happened, revealing the specific physics of the inflationary field and its energy. It would provide our first real experimental data on the quantum nature of gravity, showing that space-time itself can behave as a quantum field, fluctuating at the smallest scales. This discovery would forge an unbreakable link between the world of the very small, particle physics, and the world of the very large, cosmology, guiding us toward a unified theory of everything. These primordial whispers are part of a broader spectrum of gravitational signals, a cosmic symphony that ranges from the high-frequency chirps of colliding neutron stars to the low-frequency hum of supermassive black hole binaries, all telling different chapters of the universe's story. Two black holes locked in a final, fatal dance can release an energy greater than every star in the observable universe. This is not a hypothetical event, but a reality confirmed by the Laser Interferometer Gravitational Wave Observatory, LIGO, and its European counterpart, Virgo. Their first historic detection in September 2015 was a moment that shook the scientific world, not with sound, but with the silent ripple of space-time itself. The signal, named GW150914, was a perfect chirp, a rising frequency that matched Einstein's century-old prediction for the inward spiral and violent merger of two black holes roughly 30 times the mass of our Sun. In the final fraction of a second before they became one, these gravitational titans converted a portion of their combined mass into pure vibrational energy, shaking the cosmos. This event opened an entirely new sense for humanity, allowing us to hear the universe rather than just see it. Each new detection adds another data point, building a demographic census of black holes. We are learning that black holes come in a wider range of masses than we ever anticipated, with some systems challenging our models of how massive stars live and die. How do pairs of such dense objects even form and end up so close together? Some likely begin as massive binary star systems that both collapse into black holes, while others may find their partners through dynamical interactions in the crowded cores of globular clusters, where gravitational encounters can forge these dark partnerships. The spin of these black holes, measured from the complex waveform of the gravitational signal, tells another part of the story. Were the black holes born spinning in alignment with their orbital dance, or was their history more chaotic, with spins tilted in random directions? Each merger is a unique experiment in extreme gravity, testing general relativity in the strong field regime where the warping of spacetime is most severe. So far, Einstein's theory has passed every test, with the observed signals matching the predictions of his equations with astonishing fidelity. Perhaps one of the most profound aspects of these events is their use as standard sirens. Because the gravitational wave signal directly encodes information about the intrinsic strength of the merger, it allows scientists to calculate the distance to the event independently of light. By comparing this distance to the redshift of the host galaxy, we can measure the expansion rate of the universe, offering a crucial new method to pin down the value of the Hubble constant. How do these invisible collisions, felt across 1 billion light-years, refine our cosmic census? They reveal a hidden population of dark objects, silently shaping the demographics of the cosmos through mergers that we would never see with traditional telescopes. This ongoing symphony of collisions, each a punctuation mark in the dark, suggests that the universe is far more dynamic and violently interactive than its serene appearance suggests. Ancient star clusters drift like cosmic snow globes in the vast halos of galaxies. These are globular clusters, dense spheres of hundreds of thousands of stars, all bound together by gravity in a dazzling, ancient dance. They are fossils from the universe's youth, with many boasting ages of over 10 billion years, making them some of the oldest structures we can observe. A perfect example is Omega Centauri, a glittering behemoth visible from Earth as a faint, fuzzy patch that telescopes reveal to be a city of stars, so packed together that the night sky from a planet within it would be a perpetual, brilliant twilight. Unlike the complex stellar populations of galaxies, these clusters are often simple, containing stars born from the same primordial gas cloud at nearly the same time. This makes them pristine laboratories for studying the early universe. By analyzing the starlight from these ancient suns, astronomers can read the chemical fingerprint of the cosmos in its infancy, a time before successive generations of stars had forged and scattered heavy elements across space. The origin of these clusters is a subject of active debate. Some, we now believe, are not clusters at all in the traditional sense, but the surviving cores of small dwarf galaxies that were torn apart and absorbed by larger galaxies like our own Milky Way, their outer stars stripped away, leaving only their dense hearts behind. Others may have formed in place, condensing from massive clouds of gas during the initial, frantic period of galaxy assembly. Their incredible longevity is a gravitational puzzle. How do they avoid collapsing inward under their own immense stellar density? The answer may lie in dynamic interactions, where close encounters between stars fling them to the cluster's outskirts, creating a stable, balanced system. Some clusters are even thought to harbor central black holes, and many are known to host millisecond pulsars, the spun-up remnants of dead stars that act as precise cosmic clocks. What can these ancient stellar cities teach us about the raw conditions of the early cosmos? They are time capsules, preserving a record of the chemical purity and violent dynamical processes that characterized a younger, more chaotic universe. Their positions and motions within the galactic halo also provide crucial clues, tracing the distribution of the invisible dark matter that governs their orbits, silent witnesses to the hidden architecture that has shaped them for billions of years. Every galaxy we see is cradled by an invisible giant. These are dark matter halos, vast spherical structures that envelop galaxies and galaxy clusters, providing the gravitational anchor without which stars would fly off into the void. We cannot see these halos directly, but we map their ghostly presence through their relentless pull. The unexpected speed of stars orbiting at the outer edges of spiral galaxies provided the first major clue, revealing that a huge amount of unseen mass must be holding them in their path. This gravitational signature, the rotation curve, is the halo's first whisper. Gravitational lensing gives us another view, where the halo's immense mass warps the light from background objects, acting as a cosmic scale to weigh this invisible component. Supercomputer simulations then bring these halos to life, showing how they form the fundamental scaffolding of the cosmos. In the most successful models, dark matter is cold and slow-moving, allowing tiny density fluctuations in the early universe to grow under gravity. Small halos form first and then merge in a hierarchical assembly, building up to the massive structures that host galaxies like our Milky Way. The density of these halos is not uniform, often following a profile that is steeply concentrated at the center and gradually thinning out at the edges. This predicted cuspy center, however, is at the heart of a major puzzle. Observations of small, faint dwarf galaxies show their inner dark matter distribution appears to be much smoother, a core rather than a sharp cusp. This core cusp problem is a persistent tension, suggesting our understanding of dark matter's properties, or the complex interplay with normal matter, might be incomplete. How do these unseen spheres of influence shape the entire cosmic narrative? They are the ultimate architects. The gravity of a dark matter halo pulls in ordinary gas, creating the conditions for galaxies to form, stars to ignite, and planetary systems to eventually emerge. The size and mass of a halo directly dictate the size and type of galaxy it can host, yet this relationship is not one-way. The normal matter talks back. Supernova explosions and radiation from massive stars can push against the infalling gas, creating powerful feedback that regulates star formation and may even reshape the inner structure of the dark matter halo itself. This intricate dance between the visible and the invisible dictates the life cycle of every galaxy, from its brilliant birth to its quiet end. A galaxy can breathe out, expelling its own potential for future life in a hurricane of superheated gas. These are galactic winds, vast outflows driven by the most powerful forces a galaxy can muster. When a region experiences a ferocious burst of star formation, countless supernovae explode in quick succession, their collective shockwaves blowing a bubble and driving a wind that can rush outward at thousands of kilometers per second. Alternatively, the central supermassive black hole of an active galaxy, a quasar, can blast out radiation and matter with such intensity that it overwhelms the entire system, launching a wind that rips through the galaxy's heart. We observe these cosmic gusts through their telltale signatures in X-ray emissions and specific shifts in optical light, revealing the composition and staggering speed of the material being cast out. This process is a crucial form of feedback, a self-regulating mechanism that prevents a galaxy from growing too fast or too large. Without these winds, a galaxy would rapidly convert all its available gas into stars in a brief, brilliant flash, leaving it a stagnant, aging system. The wind acts as a galactic pressure release valve, expelling the very gas that would have formed the next generation of stars. This explains a fundamental cosmic pattern known as the mass-metallicity relation, where more massive galaxies tend to have a higher proportion of heavy elements. The reason is that in smaller galaxies whose gravity is weaker, these powerful winds can more easily escape, carrying away the newly forged metals and preventing them from being recycled into new stars. In this way, galactic winds are responsible for quenching star formation, effectively putting the brakes on a galaxy's growth and steering it toward a more sedate, mature phase of life. But the expelled material does not simply vanish into the void. These winds carry a rich cargo of heavy elements like oxygen, carbon, and iron, elements forged in the nuclear furnaces of stars and supernovae. They transport these vital ingredients across vast distances, enriching the thin gas that fills the space between galaxies, known as the Circumgalactic Medium. This process seeds the cosmic environment with the raw materials for future planets and, potentially, life. How do these cosmic gusts influence the life cycle of galaxies? They are the great sculptors of galactic evolution, the invisible hands that regulate growth and distribute the elements of creation across the cosmos. This galactic recycling of matter through winds connects to a phenomenon of pure cosmic destruction, where entire stars are methodically torn apart by the gravity of a hidden predator. A vast, invisible ocean of gas cradles every galaxy in the cosmos. This is the Circumgalactic Medium, an immense and dynamic halo of multi-phase material that stretches for hundreds of thousands of light-years, far beyond the bright disk of stars we normally see. It is not an empty void, but a galactic atmosphere, a crucial reservoir containing a significant portion of a galaxy's normal matter, the baryons that had long been missing from our cosmic accounting. For decades, this matter was virtually invisible to our telescopes, its presence only revealed when we learned to read its shadow. The key was using the brilliant light of distant quasars as cosmic flashlights. As this light passes through the circumgalactic medium on its journey to Earth, specific atoms in the gas like hydrogen, oxygen, and carbon imprint sharp, dark absorption lines on the quasar's spectrum. Each line is a barcode telling us the composition, temperature, and velocity of the gas it passed through. More recently, sensitive ultraviolet and X-ray telescopes have begun to see the faint glow of this gas directly, mapping its complex structure. This galactic halo is the stage for the most fundamental cycle of cosmic life. From its cooler, denser clouds, gas slowly rains down onto the galaxy, fueling the birth of new stars in a process known as accretion. At the same time, it acts as a sink, catching the superheated material blasted outward by galactic winds, the very outflows driven by supernova and active black holes. This constant dynamic exchange is the baryon cycle, the breathing rhythm of a galaxy. The properties of this gaseous halo are not uniform. Around a massive, quiet elliptical galaxy, the circumgalactic medium is often hot and diffuse, having been heated by eons of feedback. In contrast, the halo around a younger, star-forming spiral like the Milky Way is a turbulent mix of temperatures, with cold, dense clouds coexisting with million-degree plasma. This complex, multi-phase structure is one of the greatest challenges for our most sophisticated supercomputer simulations, pushing our understanding of gas physics, magnetic fields, and turbulence to their limits. How does this galactic atmosphere mediate between the galaxy and the vast intergalactic medium? It is the critical interface, the membrane through which a galaxy interacts with the wider cosmos. It regulates growth, stores ejected material for potential recycling, and connects the brilliant island of stars to the invisible filaments of the cosmic web. This intricate halo reminds us that a galaxy is not an isolated island, but a dynamic entity, deeply connected to and constantly exchanging material with the expansive, empty spaces around it. Two different ways of measuring the universe's expansion now yield two conflicting answers. This is the Hubble Tension, a stubborn discrepancy that threatens to crack the very foundation of modern cosmology. On one side, we have the pristine view of the infant universe provided by the Planck satellite's map of the cosmic microwave background. By studying the subtle patterns in this ancient light, scientists can extrapolate forward, calculating how fast the universe should be expanding today. This method gives us a Hubble constant of about 67 kilometers per second per megaparsec. On the other side, we have meticulous observations of our local, modern universe. Projects like the SHOES team use cosmic ladders, observing pulsating stars called Cepheids and cataclysmic supernova in nearby galaxies to measure the expansion rate directly. Their result is consistently higher, around 73. The gap between these two values is small in number, but vast in implication, and it has persisted and even grown as our measurements have become exquisitely more precise. This is not a simple rounding error, it is a 5 sigma tension, meaning the chance it is a statistical fluke is less than 1 in a million. The universe, it seems, is telling us that one of our most cherished stories, the standard model of cosmology, is incomplete. What could be causing this rift in our cosmic measurements? The possibilities are as profound as they are puzzling. Perhaps there are subtle, unknown systematic errors biasing one of the measurements, a kind of cosmic mirage we have not yet learned to see. More thrillingly, it could be a sign of new physics. maybe dark energy is not a constant but is evolving over time, gaining strength and pushing the universe apart faster than our models allow. Or perhaps there was a previously unknown type of relativistic particle zipping through the early universe, altering its expansion history in a way that the cosmic microwave background faithfully records. Some theorists even suggest modifications to Einstein's theory of gravity itself, proposing that the force of gravity behaves differently on the largest cosmic scales than we have assumed. The resolution of this tension is now a primary driving force for the next generation of astronomical observatories. The James Webb Space Telescope is scrutinizing the cosmic distance ladder with unprecedented clarity, while future missions like the Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory will map the cosmos with breathtaking scope, searching for the subtle clues that will reconcile these two conflicting realities. What does this fundamental disagreement imply about our journey to understand cosmic evolution? It is a powerful reminder that our models are maps, not the territory itself. When the map no longer matches the landscape, we are forced to explore anew, to question our most basic assumptions, and to prepare for a revelation that could once again redefine our place in the cosmos. These 25 phenomena weave a single story, from the ghostly whisper of a neutrino to the silent architecture of a dark matter halo. Each one, a thread in the same cosmic tapestry, pulls at the fabric of our understanding, revealing that our most trusted theories are not wrong but incomplete. The elegant rules of the Standard Model cannot account for the shape-shifting mass of neutrinos or the ghostly dominance of dark matter. The profound geometry of general relativity is challenged by the runaway acceleration of dark energy and the stubborn tension in the universe's expansion rate. Together, they point toward a deeper layer of reality, a realm where quantum mechanics and gravity are finally unified, and where unknown forces in a dark sector orchestrate the cosmos. The universe is not a collection of isolated wonders but a single, dynamic system, where a star's death seeds new worlds and a black hole's feast dictates a galaxy's fate. This interconnected reality, where 95% of the cosmos is made of dark, unknown components, forces a humbling admission. We have been studying the universe through a keyhole, marveling at the sliver of light while the vast, dark room beyond remains unexplored. This journey does more than advance science. It stirs profound questions about our own place in the grand scheme. Does a universe so vast and strange require an observer to give it meaning, or does it simply exist, magnificent and indifferent? The endless cycle of discovery, where each answered question births new, deeper mysteries, is not a flaw in our knowledge but the very engine of our curiosity. How will the next generation of telescopes and detectors transform our cosmic perspective? They will not just fill in the blanks on our current map. They will reveal that we have been using the wrong map all along, guiding us toward a reality more wondrous and interconnected than we have yet dared to dream. We have journeyed through a cosmos where reality is perpetually rewritten by wonders that defy our conventional understanding. From the silent, space-time warping titans at the hearts of galaxies to the inexplicable push of dark energy accelerating the universe's expansion, these 25 phenomena are not isolated curiosities. They are interconnected threads in a single, magnificent tapestry, revealing a universe that is profoundly more mysterious and magnificent than our everyday experience could ever suggest. They force us to rethink our most fundamental concepts of matter, energy, and even the nature of time itself. The cosmos operates on a logic that often transcends our earthly intuition. As the astrophysicist Neil deGrasse Tyson reminds us, the universe is under no obligation to make sense to you. Its laws are written in a language of extremes, from the quantum ghostliness of neutrinos to the silent, dominant architecture of dark matter halos. These discoveries do more than just enrich our scientific knowledge. They instill a profound sense of humility. We are reminded that we are temporary inhabitants of a small world, peering out at a reality that is 95% unknown to us. This is not a cause for despair, but an invitation to endless possibility. It is an acknowledgement that the greatest discoveries still lie ahead, waiting for the next curious mind to look up and ask a new question. We would love to hear which of these phenomena captivated you the most. Was it the phantom rain of neutrinos, the silent scream of a fast radio burst, or the humbling architecture of the cosmic web? Share your thoughts in the comments below. If you enjoyed this deep dive into the mysteries of space, please subscribe for more journeys to the edge of understanding. Keep looking up. The next great discovery, the next reality-shattering wonder is waiting.